Yeah, good morning, students. Today I'm going to explain you about one more important problem, that is drawing a shear force and bending moment diagram for a cantilever carrying uniformly distributed load of intensity small w over the entire span. Here you can see a cantilever beam which is fixed at B and free at A. The length of the beam, or you can call it as span, which is equal to L meters. Now for this beam we need to draw the shear force and bending moment diagram. So to draw the shear force and bending moment diagram, what I'm going to do here is just I'm going to consider a section in between A and B. Let the section be capital X and X. Now this section is located exactly at a distance of small x from the free end capital A. Now the shear force at any section, we can calculate the shear force at any section. I'm just abbreviating the shear force as SF. Shear force at any section X will be equal to. So what exactly is the shear force? According to the definition which I gave you, shear force is nothing but the algebraic sum of all the unbalanced forces towards left or right side of the section. Now here I have drawn a sectional line capital X and X. Now I am considering right side of the section. Now what exactly is the force which is available on the right side of the section? It is W newtons, which is acting over 1 meter. Now when you are considering right side of the section, from this particular sectional line till point A, we have considered the total distance as x, and the amount of load which is acting on this one is W Newton per meter. Now what will be the total load acting on this particular span? So it will be equal to W multiplied by x. So this will be equal to W multiplied by x. Suppose if the entire load, we consider the entire load which is acting over the entire span, then it will be equal to W multiplied by L. The intensity of load, or the total load which is acting over the entire span, it will be equal to load multiplied by the span, right? W multiplied by L. But here we need to calculate the intensity of load only over the span from the section capital XX up to point A. So it will be W multiplied by X. So shear force at any section XX will be equal to W multiplied by X. This is W multiplied by X. Now the question here is whether it is positive or negative. From the sign convention which I gave you, if I consider a sectional line towards right side of the section acting in the downward direction, we have to take that one as positive, and towards left side of the section acting upwards, we have to take this one as positive again. And what about the negative shear force? If suppose a force is acting in the upward direction towards right side of the section, it has to be taken as negative. Same, when it is acting in the downward direction towards left side of the section, it has to be taken as negative. So while you are practicing from different textbooks, some other faculty, right, will also just change the directions of the shear forces, right? Sometimes they will take this one as negative and this one as positive. Towards the right side of section, downward may be taken as negative, sometimes clockwise negative. Okay, now here we have the shear force, which is W multiplied by X. Now my intention is to calculate the shear force over different points or at different points. Now I'm calculating shear force when X is equal to 0. That means when X is equal to 0. See, we are taking section from free end. That means it will be starting from 0, right? Up to here it is X, and up to here it will be equal to L. Up to here it will be equal to L. Now here shear force at X is equal to 0. That means shear force at point A. That means we can write this one as shear force at point A. Shear force at point A. So just we need to substitute the value of X is equal to 0. This will be plus W multiplied by 0. It is equal to 0. Right? Now the shear force over here, it is equal to 0 newtons. Now similarly, I want to calculate shear force at a distance of X is equal to L by 2. Exactly in the midspan. So this will be equal to W multiplied by L by 2. So this is WL divided by 2. Now same thing again, shear force at any section X is equal to L. Shear force at any section X is equal to L. Just I am considering right side of the section. As you can see, only one force is acting towards right side of the section. The algebraic sum of all the forces, right? The intensity of load we need to calculate. That will be the shear force. Now shear force at X is equal to L, which will be equal to W multiplied by L. So we got it, right? Shear force at X is equal to L, right? So I can call this one as shear force at point B. Shear force at point B, this is equal to W into L. Shear force at point B, which is equal to W multiplied by L. So we got two different values here. Shear force at point B over here, and shear force at point A. Shear force at point A, it is equal to 0. Shear force at point B, it will be equal to W multiplied by L. Right. Now, let us go with the shear force diagram. This was the beam. This is point B. Here we have point A, on which there is a loading, which is W Newton per meter, acting over the entire span of L. Now, I told you, for a cantilever, always we have to start from the free end. Now, I'm drawing the baseline. This is called as baseline. Baseline. Now, all the values which are plotted above the baseline should be positive, and below the baseline should be negative. As we have got all the positive values here, shear force at B will be equal to W multiplied by L, and over here it is 0. Now, at point A, so this point, shear force, it is equal to 0, and exactly at point B, the shear force, it will be equal to W multiplied by L. That means I'm just marking a point over here which is equal to W multiplied by L. Now, how does it vary? See, as you can see, it is a first degree equation. You can take see the power W multiplied by L. We have calculated one simple equation here, W multiplied by X. What is X to the power? 1, right? When you see an equation which has got a power 1, right, 1 degree equation, then a variation of either the shear force or bending moment will be linear, right? When you are going with shear force, it will be linear. When this one is square, quadratic equation, then it will be parabola. Similarly, if I take bending moment equation to the power 1, if the equation has got to the power 1, I mean to say 1 degree equation, then linearly varying curve you will get. Here it will be same again, linearly varying. That means we need to draw this intensity over here. It is equal to W multiplied by L. Now from point B, I am simply joining a line to point A. This has to be a straight line. This has to be a straight line. I am just writing here straight line. This is a straight line. Now, is it positive or negative? As we have plotted in the upward direction, right, it has to be positive. Just I am marking positive over here. The shear force diagram is completed. Next, let us go with bending moment diagram. So this is SFD. I am marking it as SFD, that is shear force diagram. Now let us go with bending moment diagram, BMD. This is SFD, shear force diagram. Now bending moment diagram, same thing again. Let us consider a section. See, as you can see here, we have already considered a section X and X, which is located exactly distance of X. Now I'm generating some bending moment equation here. Bending moment at any section X and X will be equal to, see, towards right side of the section we have this intensity of load UDL. According to the definition of bending moment, it will be algebraic sum of moments caused by the forces towards left or right side of the section. Right? Okay. Now, how many forces are acting towards right side of the section? There is only one force, that is W Newton per meter. What will be the intensity of this load? Intensity of this load will be W multiplied by X. W multiplied by X. Why W multiplied by X? This entire span, it is equal to X. Span is X and load is W Newton acting over 1 meter. Right? So the total load will be equal to W multiplied by X. Now this W multiplied by X will be acting somewhere exactly in the middle over here. That means it will be acting exactly at distance of X by 2. It will be acting exactly at distance of X by 2. That means it will be equidistant from point A and equidistant from the sectional line. That means somewhere here. So this W multiplied by X by 2, right, will be our moment. But as you can see here, this UDL with respect to this sectional line X and X is trying to bend the beam in the downward direction. This entire moment, right, it is creating a moment which is bending it in the downward direction. So whatever the moment which we get here, it should be negative bending moment. So bending moment at any section XX will be equal to minus load multiplied by perpendicular distance. How much is the load? W multiplied by X. W into X is the load multiplied by perpendicular distance. At what distance it is located? X by 2, right? So it is multiplied by X by 2. So I can write this one as minus W X square divided by 2. as you can see here, right, to the power 2. So when you see bending moment equation to the power 2, then the equation will be a parabola. It will be a parabola. Now I need to calculate bending moment at any section x is equal to 0. That means bending moment at point A. So this will be minus W multiplied by 0 by 2, it is equal to 0. Right? Obviously we got that one as 0. Next, bending moment at point x is equal to L. That means bending moment at point B. So this is minus W multiplied by L square divided by 2. So this minus WL square divided by 2. Minus WL square divided by 2. So we got bending moment at point A, which is equal to 0. Bending moment at point B, which is equal to minus WL square divided by 2. Negative bending moment. That means it has to be plotted or it has to be drawn below the baseline. Same thing again. I'm drawing a baseline. So this is the baseline. Here we have point A and here we have point B. Now exactly at point A, bending moment is equal to 0 Newton meter, right? What will be the units of bending moment? Force multiplied by perpendicular distance, then it will be equal to Newton meter. It is 0, and exactly at point B we got the value as minus WL square by 2. Below the baseline we have to mark it. So this value here minus WL square divided by 2. So I need not indicate minus sign because we are plotting it below the baseline. Okay, just I am simply calling this one as WL square divided by 2. So okay, I have plotted a point below the baseline at a distance of WL square divided by 2. Now variation of the curve in between these 2 points, it will be a parabola. It will be a parabola. Now the question is, in which direction we have to draw the parabola? It should always be convex, right? Not convex towards the upward direction and concave towards the downward direction. See, look at this one and write it down carefully. Suppose if there is a baseline, always there should be convexity facing towards the upward direction, and when it is below the baseline also it should be convexity in the upward direction, right? See here, just I'm drawing a curve here which is a parabola. And nature of curve is parabolic. Now this has to be negative. I'm just marking it as negative over here. So here we have drawn the shear force and bending moment diagram for a cantilever beam which is carrying a UDL of W Newton per meter over the entire span. Right, that's it. Thank you.